that are in the new upcoming architectures, both Knight's Landing and NVIDIA Pascal. And then give you a broader context about scientific HPC and scientific supercomputing and how all the various things fit together. In the slide deck, so the slide deck has more slides than I'm going to get to. Many of the slides at the end talk about things you should know for using large-scale HPC systems, and I think those are things that will be useful for some of you, although I probably won't get to them in the talk itself. All right. And so briefly, the basic idea is you have a problem, you have a scientific problem, and you want to know how to optimize it for a large-scale computer. Now, I mean, some of you may end up getting Knight's Landing on your desktop or something, but I think most of you won't. Most of you will, if you see Knight's Landing or you see a HPC targeted GPU, it's going to be as part of a larger scale system that you're going to log into remotely. And so the first, philosophically speaking, we want to figure out what we mean by optimizing code. I don't know why it keeps turning off. Okay. And so, generically we have this idea about what it means to optimize code. And so here's the generic idea that most people have, right? So first we start with some science problem, and then we do some numerical analysis, and we choose some set of algorithms, and then we implement and we test those algorithms. Hopefully we test the algorithms. Then we optimize the code using some knowledge of the system and tools and relevant things, and then we get to run our nice new high-performance code. And of course, the problem is that this doesn't generally work all that well in practice for the following reason. And that is that the place where you need to apply the knowledge of what the system is capable of doing and how it works, this is going to get somewhat annoying, is that you really want to apply it in two different places. The first place that you want to apply it is in the step where you choose the algorithms and what you're doing. And then the second place is going to be where you are optimizing the algorithms themselves. And know why. I'm not really going to talk about these things in detail, but I put a list here of things to think about which actually are trade-offs that system knowledge can go in to help make. Things like how you choose the basis functions you're using and the resolution you're using, what kinds of representation you're using, like are you using a grid code or a particle code, what kinds of solvers you're using and how you regularize or renormalize the solutions, which degrees of freedom you compute dynamically versus which ones you evolve, and all those kinds of things. So all of these things are trade-offs, and again, I'm not really going to talk about them, but I think it's really important if I'm going to start talking about optimization in scientific computing to say that the way you make these choices is to get a really high-performance code is often influenced by the architectures you're supposed to be running on. Okay. Is my computer doing that or someone else's? Okay. All right. So let's start with a very simple example here. So most computers, okay, I'm going to be very general here, are built to do essentially three things. They are built to move data around, and they're built to make decisions, right? The code has branches and such, and they're built to compute polynomials, relatively low-order polynomials. And so here I've written down a relatively low-order polynomial. And so the first thing that we're going to do, I don't know, by the way, is it my computer doing that, or is it the system? Let's see. Yeah, okay. All right. So the first thing here is, okay, so I had my polynomial equation here. Okay, so there's my polynomial. Okay, and here I put it in some code. And then I compiled this code. And I want to see whether this is a good sort of high-performance solution to this problem. Well, the first thing that I notice when I do this is that it's not really doing a lot of useful work as I compile it. It's moving a lot of data around, and it's making calls to this power function. And these calls are expensive, and this work is not useful. And I'll start out by saying, before we go through this example, that yes, I know that if you use fast math, and that will fix this particular code example, but it's not a general solution. And so, okay, so I'm going to do a better job. So how am I going to do a better job? Well, okay, so I'm not really going to use the power function. I'm actually going to put in the powers directly. Now, of course, the power function is a fine function, but it's designed so that it can accept any like real number in that second parameter. And as a result, it's a much more generic function than you need to compute powers of x. And so this is a much more direct and more efficient solution. Okay, so now I compile this, and I have a bunch of these things. I have multiplies and adds, and that looks better. But of course, if I do this, you'll notice that I'm computing, say, x squared many different times here. And that's really not efficient either. So I'm going to go back and I'm going to do something a little bit smarter. I'm going to factor out x in the various positions, and I'm going to evaluate this polynomial in a slightly smarter way. And now the code even looks better. And I can make it look even better. Okay, so here's the code we just had before. And now I realize, oh, right, because most compilers on x86 don't by default target the architecture you're on. They target some default vanilla architecture that doesn't have, say, AVX support. And so I'm just going to put this here, a particular flag for targeting. This was on my laptop, but on the machine I happen to have. And then I will end up with a much more succinct version of the code. And this is much better. This is the code that I expected to have for this evaluation. You can see here we have these fuse, multiply, add instructions, which I'll talk about a bit later. But fuse, multiply, add in general computes this. It's A times B plus C. And the one thing I will note, as an example, I'm going to have in mind two systems here. One system are the Knights Landing systems, these new Intel many-core systems. And the other set of systems I have in mind are the systems like the ones that Oak Ridge is getting, which have PowerPC, Power CPUs from IBM, and NVIDIA GPUs. So I will mention some PowerPC-specific things here because many of you will end up running on those systems. And so here I have march equals native, and I note on PowerPC you have to use -m CPU instead of -march. It's a practical matter. Okay, so now I've made this sort of as good as I can in some. We'll find out. All right. Sorry about that. So here we have our FMAs, which again are fuse, multiply, adds, and this is the sequence of FMAs that correspond to this polynomial. But the thing to realize is that FMAs, like all floating point arithmetic, are complicated. And modern processors can't do them in one clock cycle. And because they can't do them in one clock cycle, so here I have a diagram showing a sort of generic internals of a floating point pipeline. And the only thing I want to point out to you is that there are something like 5 or 6 stages in it. 1, 2, 3, 4, 5, 6. And that's pretty general. I mean, it's the same. It works essentially the same way on CPUs and GPUs and everything else. So here's the problem. So here I have my polynomial, and here I have my FMAs, and I do this one an FMA, and then I have some intermediate result, and I use that in the next one, and this one produces another intermediate result, which I then use in the next one, et cetera. But each of these things takes something like 6 clock cycles to compute. And so as a result, this is what it actually looks like, in a sense, when it executes. So here I do the first one, and then I wait for a while it finishes. And then I do the next one, and then again, I wait for a while it finishes. And a large part of modern computer architecture deals with the following question, which is, how do I put useful work here? And a lot of the differences that you understand between CPUs and GPUs, or hopefully we'll understand by the end of the talk, have to do with different strategies that the architectures use for putting useful work in that spot. All right, so a common strategy between both CPUs and GPUs is to use hardware threads. So when you use hardware threads, and when I say hardware threads, these could correspond to lots of different things. They could correspond to different threads with Openmp. They could correspond to pthreads. They could correspond to different processes on a CPU. But regardless, each core can track a certain number of threads, and it just sort of round robins through the threads that are ready. And so in each cycle, because the different threads are independent from each other, it can use instructions from each thread to schedule useful work in between these various FMAs. And so then the question is, well, how many threads do you need? And this comes down to a question of how much latency do you need to hide between these various instructions. All right. So here I've pasted a chart, which you can find using Google. This is the latency numbers every programmer should know chart, which is actually quite convenient. I think as a physicist, I always like to see timescales. Okay, so here we have timescales, and so here we have the basic clock cycle here. So most HPC systems, the large-scale HPC systems anyway, run at close to a gigahertz, maybe a gigahertz and a half, something like that. And so the characteristic timescale there is between a half and 1 nanosecond. That's the time it takes for the processor to go through one clock cycle. And then there are a number of other timescales here which are relevant. So the data that comes in from the L1 cache, for instance, is generally resolved in a pipeline fashion in one clock cycle. But from the L2 cache, for instance, takes about 25 to 30 clock cycles. Likewise, from main memory is a factor of 4 or 5 more than that, or I should say, I'm sorry, is about a factor of 100 more than that. And so on and so on. And so you can see here the various timescales for doing things like reading from disk and communicating over the network, which I think are quite helpful. And just to give you a feeling about how HPC network, the networks on supercomputers and HPC systems fit in, here I have a slide talking about the IBM Blue GQ network, which is the production system at ALCF currently. And you can see here that the best sort of neighbor-to-neighbor communication is about 80 nanoseconds. So that's about 80 clock cycles on that system. But in the worst case, it's about 3 microseconds. And in fact, the MPI neighbor-to-neighbor communication is about 2.2 microseconds. All right. So at this point, we now have this bifurcation. We have these two swim lanes, as we call them, to exascale, and one of them is to use many-core CPUs, and the other is to use GPUs. And again, both these two systems primarily differentiate on the techniques they use to put useful work in between those various dependent instructions. And so here, the basic parameters here. Many-core CPUs, just like most other CPUs on the market today, support a small number of hardware threads. Nice Landing, for instance, has 4 of them. Blue GQ also has 4 of them. Many processors now, just commodity processors in your laptop may have about 4 hardware threads per core. And they rely on other things to make up the difference, things like out-of-order processor with branch prediction, techniques that the compiler can apply, like loop unrolling and vectorization. Whereas GPUs take a different approach. The GPU approach is to have many more hardware threads, and to use those hardware threads to hide the latency. So it's a simpler approach. It's easier to explain, and it's sometimes easier to teach. There are techniques that they have to use in order to reduce the amount of state that the processor needs to carry around for all these threads. And one of these things, which I'll talk about later, is this SIMT approach, where different hardware threads on the GPU share the same instruction stream. And this is a great approach for GPUs because they're all about throughput, and they don't necessarily have to be concerned about latency of individual operations like CPUs do. Okay, so in this talk, I'm going to go back and forth between a number of different things. And so here I'm going to talk a little bit about the threading on GPUs and how that works, specifically in terms of CUDA. If you're using OpenCL for AMD GPUs or something like that, then it's similar. Okay, so the first thing is that the threads, you have a lot of hardware threads. And these hardware threads get arranged into a kind of, by a geometric decomposition. They get decomposed into grids. The grids themselves are decomposed into blocks. The blocks essentially have a three-dimensional decomposition, which is really nice for us as scientific programmers because we often have 3D spatial things to decompose over. And so the mapping is quite natural. And the size of these blocks, however, is limited. On modern GPUs, it's limited to about 1,000 threads per block. And it's only within each block that the threads can actually synchronize, which means it's only within each block that the threads can sort of directly share data. So the threads are then decomposed into what NVIDIA calls warps and what AMD calls wavefronts, which are small groups of threads that essentially execute at the same time on each core. And these things share the same instruction stream. In other words, there's one set of instructions, and all these threads need to be executing the same instructions in sequence. And this is nice because the processor then doesn't have to keep track of all of the different things that different threads might be doing at the same time. But it does lead to a challenge from the programmer's point of view. And the challenge is that these threads, if they have to share the same instruction stream. And that means that it is fine if they're actually doing the same thing. But if there's any kind of branch, if there's any kind of divergence between the threads where some of them want to do one thing and some of them want to do the other, then you end up with a performance loss because all of the threads in this group, in the warp, in NVIDIA's terminology, have to, like the threads that are doing this first part here are doing it, and the other ones are essentially waiting. And then you get to the second part, and then the threads that executed path A here, they wait, and the threads that needed to execute path B, then they get their turn. And so when you have this kind of divergence, it leads directly to a loss of useful work. And so this is the trade-off that you have to put up with if you want to use modern GPUs, is that you need to arrange your work so that there are a lot of threads that are doing, to the extent possible, all of the same thing. This is those thread groups are being executed by what NVIDIA calls a streaming multiprocessor, which everyone else calls a core. And you have a number of these on each GPU. So here I pointed out, so on the Kepler GPUs, which is what the supercomputer Titan has, for instance, there are about 15 of these per GPU. The upcoming Pascal GPUs have 56 of them. So it's more, and this is a picture of Pascal, and so you can see each of these sort of regular blocks here is one of these streaming multiprocessors. And each of these streaming multiprocessors, if you blew it up in diagrammatic form, looks like this. They have a number of these cores with these various units. Each of these can hold a certain number of warps, maximum of 64 of them. And there's a maximum number of blocks that all share the same kernel that you can assign to each of these things. Here on Pascal, it's 32 of them, for instance. And they have a number of sort of auxiliary things, like there's the register file here, which I'll talk about in a bit. And there's the texture memory here, which is really useful for read-only data. And one of the things that often bites people when they run on GPUs is this issue of registers. So when all of the threads, each thread is doing its work, like computing these FMAs, and it has to compute these sort of intermediate values. And it stores these intermediate values in registers that are associated with each thread. And so the question is, how many registers can you have? Or essentially, how many threads can you run at the same time? And the number of threads you can run at the same time is in part limited by the number of registers that each one of them uses. Because the core has a single register file that gets divided among the different threads. And so since efficiently using the GPU is so tied to having lots and lots of hardware threads, it's really important that you can run as many of them as possible. And you can often find yourself in a situation where you're limited in the number of threads you can run by the number of sort of intermediate values that each of them needs to store. And so the compiler by default will not necessarily do a very good job of limiting this. And so it's important to figure out how many registers you have, how many registers your kernels are using. And if you like, you can see documentation on various pragmas and things that you can help direct the compiler to produce kernels that only use the appropriate number of registers. All right. So now I'm gonna jump over and talk about CPUs for a moment. CPUs have to use a slightly different technique since they have many fewer hardware threads. So here I have an example. This first one is on loop on rolling. So here I've taken my FMAs here and I put them in a loop. And this loop is reading data out of some input array and writing it to an output array. And here I've applied a technique which the compiler will likely apply for you to some extent, although some tuning of exactly what factor is used is often something that a person needs to do. And so here I've taken this and I've unrolled by a factor of 2, which means I've taken 2 loop iterations of this loop and interleaved them so that they execute at the same time. And so since each pair of these things is independent, there's no waiting that has to go on in between these. And if I'm just hiding the latency from these FMAs, then I probably need to unroll by a factor of 6 and not 2, but that wouldn't fit on the slide. And so the amount you can unroll and the amount you can do many other things is going to be limited by the number of registers you have. And so here I've come back to this point. On an Intel chip, there are about 16 general-purpose registers. Those are the ones that hold integer values and such. With AVX512, which is what you get on Knight's Landing, for example, you actually have 32 floating point and vector registers and 8 mask registers. And most modern architectures have somewhere between 16 and 32, maybe even 64 registers. That's the common range at this point. And another thing which is really important to understand the performance of code on an architecture like Knight's Landing is to look at the fact that it has out-of-order execution. Out-of-order execution means that the processor can run through and start executing instructions before it finishes executing even instructions that they depend on. And it can do this speculatively. So here, for example, so here, for example, the processor might start executing the first iteration of the loop. It will get to the ending of the loop. It will predict that you're going to go back to the beginning of the loop and start executing the next iteration of the loop, even before it finishes the first one. It can do this to a limited extent. And the limited extent has to do with the number of what are called renaming buffer entries, of which Knight's Landing has 72, which is essentially how many registers can it rename, how many internal registers does it have to start executing these instructions that it's doing speculatively. And also reorder buffer entries, again there are 72, which is how many instructions can it kind of start executing outside of their sort of normal order in the dependency chain. And so here you can see, and part of the reason you need this is because the pipeline here for a Knight's Landing chip can execute many instructions at the same time. So the instructions come in here, it can essentially decode 2 of them in every clock cycle, and then they get dispatched to many different pipelines. So you can dispatch 2 per clock cycle to the memory, load store pipeline. You can do 2 of these integer instructions and 2 of these vector instructions. And so in order to sort of be able to do this aggressively and then clean up after the fact which instructions actually finished first, you need to have this out-of-order execution capability. Now, I mentioned vector instructions, and vectorization is obviously quite important on modern CPUs to get performance. And vectorization essentially works like this. Within the vector unit, there are a number of essentially identical pipelines, sub-pipelines, that can execute different operations per vector lane. And so what does that mean? Well, it means that for an operation like this, where you have a multiplication and you end up with a result, the compiler will hopefully auto-vectorize this, and you can end up doing many multiplications at the same time and get many associated results. And the vectors on modern processors, BlueGeneQ accepted, the vectors are of a certain length, and they can be divided in many different ways. Different instructions treat these vector operations, treat the vectors as holding different kinds of data. So, for instance, a 128-bit vector might hold 2 double precision numbers, or it might hold 4 single precision numbers, etc. Now, Knight's Landing supports a number of different vector instruction sets because it's x86, and you can essentially run all of your previous x86 code on Knight's Landing as well as the new stuff. And so here, this is a slide from Intel, you can see that the Knight's Landing supports lots of the old vector instruction sets and also these new AVX512 things. And the AVX512 support includes a number of sort of new features that were not available previously. Of note, Knight's Landing supports particular acceleration for various transcendental functions like exponential, logarithm, in addition to things like square root and such that have been supported before. And it has scatter-gather support for loads and stores, which I'll talk about in a second. I'm going to skip this in the interest of time. So one of the new features that AVX512 has is it has these mask registers and can do masked computation. And what that means in practice is, so here's an example of an add. So we're adding these two vectors together. There's an add, but the result here is masked. So in other words, we do the addition here. We do this addition, but we only keep some of the results depending on the setting of the mask register. Now that sounds that's interesting, but one question is like why does that matter? Like what does that do for you? Well, the masking doesn't just only keep some of the results. It also hides some side effects. So for example, if you're doing a load and some of those elements may have caused a segmentation fault, but you've masked them off, then you don't see the segmentation fault. Similarly with floating point exceptions. And so I'll skip this too. What this enables you to do is it enables you to easily auto-vectorize loops that could not vectorize before. For example, so here I have a loop. It's going over some arrays x, y, and z. The motivation for this example is a particle code where you're doing like you have some particles and you have some softening length or what have you, and then you're computing some interaction. And this is a sort of quite common modality where you're computing a radius value, you're comparing against the softening length, and this code would not previously auto-vectorize. And the reason it wouldn't auto-vectorize is because you would only conditionally dereference this V array here. And there was no way for the compiler to vectorize this and also prevent this code from segfaulting in a particular sort of hypothetical situation, but one that the compiler had to deal with regardless. And perhaps it's worth understanding what the situation is. So here I have my arrays, and I have a loop, and the loop goes from I equals 0 to n, and it computes a radius from this x, y, and z values, and then it does something if the value is, say, greater than a softening length. And if it is greater than the softening length, then we call f of v whatever. And so here's the problem that you'd end up with. So the problem you'd end up with is hypothetically speaking, let's say this v array wasn't as long as the other ones. And I just so happened to arrange it so that even though this array wasn't as long as the other ones, for all of the invalid index values for v, it just so happened that x, y, and z were all 0, say. So this condition was always false, and you would never actually dereference any of the sort of illegal values of v. So this is the situation that the compiler had to protect against, and this is why it would not vectorize that loop. I also just want to take a small digression here and talk about the fact that in this example I put the restrict keyword on these arrays. And I'll say in C++, you can also use this on essentially every compiler. You just have to put underscores in front of the restrict keyword. And I just want to explain to you what restrict actually means. So the definition of restrict is as follows. It says that within the scope of the restrict variable, which in this case is the entire function, since these are parameters, you are making the following promise to the compiler. You are promising that any memory that you access through these pointers, or any pointer you derive from them, you will not access through pointers that you don't derive from these values. I wrote this definition here. You might want to think about that, and I can answer questions about it later. But a lot of people misunderstand the semantics of this, and I think it's important that you take a minute to understand what those actually mean. Okay, so I apologize. I am rushing somewhat. Okay, so let's go back and talk about generically sort of what programs do, so we can move on to the next topic. So most programs, they read data from memory, and then they do some computation, and then they write data back to memory, and they probably communicate with the outside world. And so the next thing we realize, of course, is that we've talked a lot about the compute part, and now we're going to talk some about the memory part. So here I'll go back to my example of Knight's Landing. Other architectures are similar. Each core on a Knight's Landing machine, of which there are 60-something or 70-something or what have you, are arranged into these tiles. The tile has 2 cores, and they share this level 2 cache. Now, but each core has its own level 1 cache. The level 1 caches in this case are about 32 kilobytes, and the shared L2 cache is about a megabyte. And the cache is write back, which means that to write data into memory, you first have to read it into the cache, and that's something which is sometimes relevant to keep in mind. I will mention that on NVIDIA GPUs, there's a similar concept to this L1 cache, but it's explicitly managed, not automatically, and it's called shared memory. Okay. And so how does this work? So when you issue a load from the CPU, that request goes to the L1 cache. If the data is in the L1 cache, then you're good. If it's not in the L1 cache, then it will request the entire cache line containing that data from the L2 cache. And the L2 cache, if it's in the L2 cache, then it sends the data back. If it's not in the L2 cache, then it requests the entire cache line containing that data from the memory controller, which has a small reordering buffer, but otherwise issues the request to your DRAM. I will mention this coalescing buffer, which does exist on both CPUs and GPUs, is generally larger and will wait for longer on GPUs because they can hide more latency. Okay. So I'll come back to the DRAM bit in a minute, but first I want to mention something that's sort of new about the Knight's Landing chips. So the Knight's Landing chips, you have a bunch of these tiles. Each tile had 2 cores, and they're arranged onto this big mesh, which is connected by this special on-chip network. And at boot time, you can select 3 different potential modes for this mesh. And this is really important for how you access memory. Each of these things has its own L2 cache, but the memory system in general is coherent, which means that when you make a request, if that cache line is present in some other tile's cache, you need to fetch it from there instead of going to memory. And so that means you need to keep track of which tiles have which cache lines. And for that, they have these things called tag directories. And the way that the memory addresses are assigned to the tag directories is different in the different modes. So there's an all-to-all mode, which is a sort of generic best guess random distribution, in a sense, of all addresses to all tag directories all over the chip. There's a quadrant mode, where you divide things up further. And then there's a subnuma clustering mode, where each of these quadrants actually looks like their own NUMA domain. And I will caution, this mode does have advantages, or potential advantages. It also has some sort of hidden disadvantages. So one hidden disadvantage of this mode, in which each of these quadrants is explicitly exposed to software as a NUMA domain, is that the quadrants aren't symmetric. So you'll notice there are 2 memory controllers that actually sit in 2 of the quadrants and not in the other 2. And this can lead to observable effects. Okay. So the other interesting thing about Knight's Landing is that it has this thing called high bandwidth memory. High bandwidth memory means that there's memory that's actually on the package with the core, and in this case, there's 16 gigabytes of it. You can arrange this, again at boot time, in essentially 3 different ways. You can have it in cache mode, where the on-package memory, the 16 gigabytes, serves as a direct map cache of the off-package DDR. You can arrange it into what's called flat mode, where the different kinds of memories just occupy different parts of the address space. And you can choose a hybrid between the two. And so if you have this in cache mode, then you don't do anything special. You just run your application, and you'll get whatever performance you get out of that. But if you have it in flat or hybrid mode, then you need a way of allocating memory either in the fast memory, the on-package memory, or in the off-package memory. And for that, Intel has developed a library for C and C++ called memkind. And so you can allocate memory in the high bandwidth memory by using this HBWmalloc function. And for Fortran, there's a special attribute that Intel has developed that enables you to allocate memory in the high bandwidth memory. So on this front, I'll then go and mention something that's new on the GPU front in this regard, and that is unified memory. So the GPU used to have its own memory space, and with CUDA 6, which was available on Kepler, they did introduce this so-called unified memory, which is a sort of transfer on demand. But it was limited to the amount of memory that could fit on the GPU, and it was otherwise inconvenient to use. Whereas, I'll show you what I mean in a second. So here there's some code that uses unified memory in the sort of old system, where you had to allocate the data in a special way, and you had to do particular things to synchronize the data. Now here, this is the sort of unified memory in the new view, and the reason it's convenient to use is because you don't have to do any kind of special allocation. So and it's also can access any data on the system anywhere. You can allocate your data just with normal malloc or whatever method you normally use to allocate memory. You can then use it directly on the GPU. In other words, the pointers on the GPU and the pointers on the CPU are now the same. So you don't have to worry about deep copies. You don't have to worry about any of that stuff. All the data gets transferred on demand. Now, for particularly high-performance regions of your code, you may not want it to just be transferred on demand. But for all the sort of other data structures you might want or need access to from the GPU, this is really a nice solution. Okay, so let's go back and talk about different kinds of parallelism, and we've talked about several of these. Obviously, the top level of parallelism is using MPI across nodes. Then you often have parallelism across sockets within a node. Now, on the KNL or on any of the many core machines, there's normally one socket on each node, so this is not really relevant. Then there are multiple cores within each socket. There are multiple, you have multiple pipelines within each core, and the hardware threads sort of fit in here. If you have SIMD, then you have multiple vector lanes within each pipeline. And then finally, there are special operations that perform multiple operations at the same time, like this use multiply add. And so the speed at which you can compute is essentially bounded by the amount of parallelism you can exploit, previous slide, times the base clock rate. And the base clock rate on modern architectures has settled out to a little less than 1.5 gigahertz, and we don't see that changing significantly in the near future. Okay, and the final thing that I'll sort of mention in this regard is the hardware prefetcher. So the systems have hardware prefetchers, so on a CPU there's an L1 prefetcher. What that does is it's hardware that monitors the memory requests that are being made, and if it sees a pattern, like you're accessing some contiguous array, it will try and request data before you actually need it, so that by the time you need it, it's in the cache already. The L2 has a similar similar feature. And there's a limited number of streams that are supported in these devices. Because remember, they're looking for consecutive requests, but from different threads and different operations in the same thread, the requests don't necessarily exactly come in order for each stream. So, it can track only a certain number of these things. On the KNL, the Prefetcher supports 48 independent streams. And remember, that's shared between both cores in the tile. So if you're running 4 hardware threads and you have 2 cores in the tile, that leaves about 6 streams per thread. And that's an important thing to keep in mind. It bears on this design decision. So often when you have arrays in your program, you have to choose between a structure of arrays layout and an array of structures layout. And so here I have this in code. With structure of arrays, you have a bunch of arrays. Like here I have a bunch of particles, and I have an X array with all the X positions, and a Y array with all the Y positions, etc. And here I have an array of structures where I have a structure that represents each particle, like X, Y, Z, and maybe a mass or whatever, and I have an array of these things. Now, the traditional advantage of this was that it's easier to vectorize, because these things, it's quite easy to load, like, some number of x's at a time, some number of y's, and do whatever you're doing just n times at the same time. And the array of structures was harder to vectorize, but it has better cache locality, and uses fewer prefetcher streams. So here, if you're doing some operation on all these arrays, you're essentially going to use 1 prefetching stream per array. So that's going to limit the number of arrays that you can effectively put in any particular loop, for instance. Whereas this would have only 1 prefetching stream necessary, so that's good. And with the new scatter-gather support with, say, AVX512, this actually might not be so bad in terms of vectorization. It wouldn't be quite as nice as this, but with the additional cache locality and the fewer prefetching streams necessary, it might be a win to use this kind of layout. And so just some general notes on compilation. When you compile your code, if you're interested in performance, I recommend turning on the optimizer. There are many compilers that default not to have the optimizer on by default. And so if you compile the code that way, then it will run very slowly. -03 is the sort of default good optimization level for scientific code. I recommend trying this first. As a practical matter, most compilers are actually best tested at this optimization level. So you often end up running into fewer compiler bugs that way, too. I also always recommend using -G, which turns on debugging symbols. Especially if you're on a large-scale system. It's really annoying when your code runs for many hours and then crashes and you don't know why. When your code crashes and you get a core dump, if you have debugging symbols in your executable, you can hopefully figure out at least where it crashed. And if you don't, then you're stuck. If you have Openmp in your program, then you have to turn it on. -F Openmp is the flag that most compilers use for that purpose. And the other thing is that most compilers by default will give you strict IEEE floating point semantics, which is not normally necessary for most scientific programs. And there's a fast math flag which will turn those off and enable the compiler to do extra optimizations that will give you more performance. Okay. So I'm going to run through a very quick example of sort of what optimizing or tuning a code might look like. And so here I just have a simple loop. It accesses some arrays and does some computation. And so I'll just run through some example logic that one might use. If you're doing this in real life, you would actually test these things. And we might go through something like this in the focus session later. So here I have a loop. It's accessing a number of arrays. So just for argument's sake, I'll say, oh, and here I've parallelized the code with Openmp. So just for argument's sake, I'll say that this might be using too many prefetching streams for each thread, because it's using one stream per array. I can easily run out. But these statements are actually independent. So in this case, I'm just going to split these into 2. And now I realize, well, actually, I went a little too far, because I split them into 2 things, but I've now split them into 2 different parallel regions, which means the threads have to start up, and then there's a barrier here. And even if there weren't a barrier, there's still some overhead to doing it this way. It's better just to have them in one parallel region. So here I've grouped them together into one parallel region that now has these 2 things. I can even eliminate the barrier here, but I won't talk about that right now. So So then, okay, so now I'm left with two loops like this. The compiler will probably unroll these a little bit. The compiler might not pick the best unrolling factor for your code. Most compilers support some kind of pragma to customize the unrolling factor. If you have a loop that's particularly important in your program, it's probably worth trying a few values to see if you can do better. Okay. A couple other notes about Openmp. By default, like if you just put Openmp parallel for what have you in your program, it will give you a static decomposition. So static decomposition means whatever range of indices your loop uses, it will just divide them by the number of threads you're using, and each thread does that number of iterations. So that's great if the amount of work is the same for each iteration. But often in practice, the amount of work is not the same for each iteration, and so you need a way of dealing with that. So Openmp is actually really nice. It has a very nice solution for dealing with that. You only have to add a few keywords, and it does some magic thing, which is that instead of dividing up the work ahead of time, it divides up the work dynamically. And so here I have an example. So here I have these threads. They're each getting the same number of iterations, but the amount of work per iteration is not the same, and so you end up having a lot of waiting. Whereas here, if I put on schedule dynamic, then the iterations get divided up dynamically, and the work is much better balanced. Another thing I'll mention is that starting with Openmp 4, there are also specific directives in Openmp for turning on vectorization. And you can use them both by themselves and also in conjunction with the normal things for threads. So the issue of using coarse-grained versus fine-grained parallelism often comes up in this context, and I'll touch on it here. So what does this mean? So generically speaking, if you're using, say, Openmp or some parallelization scheme like that, then your program starts, and it's a serial program, and then it starts some threads, and it does some parallel work, and then they all join together, and then they're done. So the question is sort of how much work do you do in each of these things? And it often happens that people will end up putting parallel regions around sections of code that are too small. And so the code will essentially spend all of its time starting up and shutting down threads, and the Openmp just won't be worthwhile. And so the generic rule here, unless there's some particular reason to do otherwise, is that you want to parallelize the largest regions possible, right? You want to use coarse-grained threading, not fine-grained threading. I will add, however, the fine-grained threading works much better on GPUs than it does on CPUs. And generically, part of the reason you want to have the largest regions possible parallelized is because of this thing called Amdahl's law, which essentially says that if you have serial regions in your code, then eventually, as you parallelize more, they come to dominate your total runtime. It's actually a fairly intuitive statement. And so, as a quick example, if 5% of your program has to be serial, 5% of the time that it spends executing has to remain serial. It can't be parallelized. Then, no matter how much you speed up the rest of the parallel regions, you'll only ever get up to a 20x speed up over the original program, because all of your time will just be spent executing those serial sections. I'll also mention quickly that as an alternative to Openmp, starting with the upcoming C++ 17 standard, there will be a whole list of algorithms that have built-in parallelization, including some basic ones like for each. And so you'll be able to, if you're more comfortable with C++ than you are with Openmp, you'll be able to use a sort of native C++ parallelization solution that will integrate nicely with the rest of your code. Okay. And Openmp is also evolving towards using accelerators. So what this means in this case is that Openmp supports not only parallelizing on the host, on the CPU, as it always has, but also supports taking data and shifting it to an accelerator and executing it there. And just as a quick example of what this looks like, if you have, okay, so here's some basic code. It has a loop. And now I've put some additional pragmas in to tell it which data needs to be transferred, say, to a GPU, and then how to parallelize it. I'm not going to have time to talk about this in detail, but this is sort of upcoming. We don't really have a lot of implementations of this feature of Openmp yet, but a number of vendors are working on this. And in the next couple of years, this is going to be an option for targeting GPU systems as well. One question that has come up already is how does this Openmp accelerator support interact with the unified memory that is going to be available on high-end GPUs? And the answer is we don't know yet. So, another sort of basic piece of advice that I'll give is on essentially all systems, vendors provide some highly optimized implementations of basic things like dense linear algebra and FFTs, and you should really use them as opposed to trying to roll your own. The MKL on Intel systems is really quite good. SL on IBM systems similarly, and NVIDIA also provides kernels for BLAS and FFTs, et cetera. Also for FFTs, I will mention that if you, unlike for dense linear algebra where there is sort of a standard set of BLAS routines, for FFTs there really isn't a standardized interface, but both Intel and AMD and IBM, et cetera, they all provide FFTW compatible wrappers for their libraries. So if you code using FFTW, then aside from like switching a header file or something, you actually should be able to directly use these optimized implementations, which is quite nice. Okay, and another question which often comes up is the choice between using threads and using multiple MPI ranks per node if you have an MPI application. And I've mentioned here a number of considerations. Mostly it comes down to memory. If you use multiple MPI ranks, you normally have ghost regions that you need between ranks. Those obviously take up memory on each node if you have multiple ranks per node. And also the sort of underlying components of MPI often have like order n data structures. And so if those order n data structures have to be repeated per rank, and so globally that's actually an n squared memory use as you increase the number of ranks. So you have to be careful about that as well. But in the end, you're likely to you'll get the best performance for whatever actually fits in memory based on which has the best, which scheme exposes the most overall parallelism. And since with MPI, everything starts executing in parallel by default, most people find that as long as the problem fits, they actually get better parallel performance from using more MPI ranks than they do from using more threads. Okay, and also most codes need to do some kind of I/O, and I'll mention a few quick things about this. One is that when you're running a large-scale application, I/O often becomes a sort of unfortunate bottleneck. You should remember to use collective I/O or some library that will do that for you, like HDF5, if you're writing small amounts of data. If you're writing large amounts of data, you probably don't want to use collective MPI/O. You just want to have a file format that gives each rank its own spot on the disk to write to. And I highly recommend, making sure your files can be validated, like store CRCs or checksums or however you want to do it. I actually have an open source library here that does this quite efficiently if you're interested in that. And also, if you're writing your own files, it's much better to make them write optimized than read optimized at scale. Most people end up writing more data than they read, plus writing is slower than reading on parallel file systems. And so you don't want to be bottlenecked on, say, writing checkpoints. Another thing that I'll mention, just as sort of a general note, is that it's often quite useful if you can statically link your applications as opposed to dynamically link them. On many systems, by default, it will dynamically link your applications, which means that your application depends on a number of shared libraries that all have to be loaded on every rank when your application starts. And this actually puts a lot of load on the file system, which is often unhelpful. The same is true in spades for scripting languages. So if you're trying to, say, run a Python script on 100,000 nodes, you may often find that it takes several minutes to load all of the Python libraries and such off of the file system. And so you'll want to have a better solution for that. Okay, where am I now? It's 5:20. Okay. So I'm just going to kind of give a quick overview of some of the various systems that are upcoming and how scientific HPC fits in this space. So I'm not going to talk about this in detail, but I'll say that at ALCF at Argonne, where I work, we have a progression of systems that we're getting, which are typical of modern large-scale systems that are coming online, which is that right now we have a system that has on the order of 10 petaflops, and over the next few years, we're increasing that by an order of magnitude. So you should expect over the next few years to have an order of magnitude increase available in the amount of compute that's available, and a similar order of magnitude increase in the amount of RAM that's on these systems. And from our perspective, hopefully not an order of magnitude increase in the amount of power they consume. And these systems, they run applications from a large number of scientific domains, which I've listed here, and they end up being fairly evenly distributed among these things. I'm not going to talk about these in detail, but this is an interesting set of slides if you want to look at it later. Interesting set of tables for these various sort of common solver techniques. It lists here how they tend to be bound. Like dense algebra tends to be bound, compute bound. Some of these things tend to be bound on memory bandwidth, et cetera. But again, for most application codes, it's when you set out to optimize them, it's important to understand what's going to be their sort of limiting resource. And generically, we group these into three categories. One are compute-bound applications. Those are applications that are bound by the amount of compute capability available on the system. There are memory bandwidth-bound applications. These are applications that are bound on their ability to transfer data from main memory into the CPU. And then there are latency-bound applications. And those are applications that are bound based on the amount of time it takes for non-contiguous memory requests to be served by the memory subsystem. If you're doing a lot of random access and arrays, you're going to be here. Most people in HPC use C or C++ or Fortran for reasons that I think are still well understood. Most people are using MPI on large systems with some amount of Openmp. For threading, Openmp by far has the majority of the market share, which is why Openmp was used in the example from the slide, and why if you're looking at a threading technology to use in your code, at least on that basis, I recommend looking at Openmp. I do want to say a quick word about challenges for the future. The largest challenge that we see for the future of supercomputing has to do with data movement. And this is a chart which I won't go through in detail that sort of explains why. But in summary, it takes far less energy to actually do a computation, say a floating point computation, than it does to move the data to the CPU to do that computation. And most of the work on modern supercomputing architectures are built around tackling this challenge. And this also explains many of the features that make supercomputers hard to use. But it mostly comes down to this. It comes down to the fact that data movement is just so expensive relative to the compute. We can provide you with a lot of compute, but it's really hard to provide the ability to get the data to the cores without exceeding the energy budget we have for the machines. All right. So I have a set of slides after this that talk about advice for running on large-scale machines. And I can do that. But before I do that, let me stop here and see if there are any questions. Go ahead.
How much of the optimization techniques you covered can be done by the compilers today?
There are some optimization techniques that the compilers are really good at. So for instance, loop unrolling and loop vectorization, compilers will often do a pretty good job at now. especially with some of the features in the AVX512 instruction set for Knight's Landing, specifically the scatter-gather instructions and the predicated loads and stores. Auto-vectorization tends to work pretty well. I don't know of anyone who thinks that compilers do a good job of auto-parallelizing code. So in terms of inserting Openmp pragmas or using whatever other scheme you're going to use for that, there are many compilers that claim to have auto-parallelization support. I don't know of anyone who uses them in practice. It's a really hard problem to get right from the compiler standpoint. There's a lot of sort of tricky cost modeling there. So I understand why it doesn't work well, but nevertheless, it's really something you tend to have to work out manually. And similarly for GPUs. So if you're targeting GPUs, that's sort of another form of auto-parallelization in a sense. Yes, there are compilers that can help you with some of it. If you use Openmp or OpenACC or what have you, that might be able to get you reasonable performance on a GPU, but it often might not. And so, again, using CUDA or some, you're going to have to help the compiler to do that kind of GPU targeting. And even for things that compilers normally do pretty well, like vectorization and loop unrolling, for GPUs, selecting the number of registers that you have per kernel, it's often, if there are particular parts of your code that are important, which you should determine by profiling your code, then it's worth sort of playing around with those pieces of the code because the compiler is using some set of heuristics to kind of guess what the best answer is going to be. It's not measuring the best answer. And so for some of these things where there are sort of a small set of parameters like register limits and unrolling factors and such, it's often worthwhile to just play around with it a little bit and see if you can do a better job than the default heuristic. Oftentimes you can. It's not worth doing for everything. But.
Can you explain how the scatter-gather instructions work on this next machine? What do they actually do?
So the scatter-gather instructions will take a vector of pointers and will load or store a vector of values based on the vector of pointers. That means that normally when you do a vector load, say, right, you give it an address, and it loads from that address the next n elements into a vector. The scatter-gather support means that you can give it a vector of pointers, a vector of n pointers, and it loads n values. Now, these things aren't entirely magic, right? So if each of these pointers is going to be a separate cache miss, then it's going to take a long time for this instruction to complete. But if the array you're accessing is in cache, then this can actually be quite convenient. And so you can, yeah. Then is it? On what? I'm sorry?
To get good performance on GPUs, sometimes people have recommended, changing to using radical sorts or using pointer-free algorithms or doing crazy things like this. Is that sort of level of data structure surgery still necessary? Because it's very painful.
Yeah. So I'll give you sort of a non-answer, which is yes and no. GPUs are much better than they used to be. So for example, it used to be the case that if you had you had divergent control flow on a GPU, and so there was a branch, and there's one side of the branch that none of the threads took, and the other side all the threads took, you would still kind of wait on the side of the branch that none of the threads took, right? That kind of stuff hasn't been true for 10 years. So there's a lot of sort of intuition which is old, but it is still true that if you're doing a lot of, say, pointer chasing on a GPU, then you may find it difficult to, even on the GPU, hide all of the latency associated with the pointer chasing. And it only really works well if each thread doing the pointer chasing is chasing the same number of pointers, because they still have to be doing essentially the same thing at the same time. So having pointer-free data structures, for instance, isn't necessarily as important as making sure that there's not divergence among the threads in whatever it is they're doing. So it really depends on why you why do you want a pointer-free data structure, right? So if you have a hash table, for example, then you're probably going to have a problem, because the hash lookup, like if you have an open addressed hash table, each thread is probably going to do a different number of like pointer lookups as it finds the slot in the hash table. And so you could end up with a problem. I think that's what it comes down to. It's also true that you may make a different decision on, say, array of structures versus structure of arrays for GPUs. Because oftentimes people choose structure of arrays because it's easy to vectorize. But that really isn't important on the GPU. What's important on the GPU is that if you have contiguous memory, you want different hardware threads executing at the same time, pulling different nearby regions of that memory. Because this is this coalescing issue, right? Because those requests will go into the reorder buffer, which will put them together and efficiently issue a minimal number of requests to the RAM. And so you arrange the code a little bit differently than you would for a CPU, where you would want individual threads to access contiguous regions of your memory. So I think like understanding those two particular architectural concerns and understanding like how they will apply or not apply to your problem tends to be more important than like fancy implicit data structures. But oftentimes, if you do have a thing like that, then you may need to use some of those data structures because those are the best alternatives.
So your last comment speaks to my question, which is how portable will code be between Knight's Landing and the next generation GPUs? Can we just write MPI and Openmp and get good performance in both? Or are we really going to have two different software stacks, one for each kind of architecture?
I think it's really going to depend a lot on the application. I think that and it's also going to depend a lot on how good the compilers are that target the GPUs, which we don't know yet. So I would like to say that yes, it's going to be. You're going to have performance portability, right? That's obviously our goal. I think in practice, you're going to end up with sort of a hybrid solution, right? You're going to have a lot of like the particularly hot regions of your code. You may make different tuning decisions around. I think the underlying goal is that using something like Openmp that can target both GPUs and CPUs, you'll be able to restrict those tuning decisions to some data structure modifications and some different pragmas, as opposed to having two completely different like branches of your code. But I still think you are going to see some, like, you will end up with different, I think regardless, you're going to end up with different tuning decisions for the two different targets, and you'll have to deal with that somehow. Okay, so for the first question, for floating point operations, the CPUs and GPUs essentially perform things about the same amount of time. Well, this is also true for integer operations as well. So floating point operations generally take about 5 or 6 clock cycles to complete, which is going to correspond to like 4 or 5 nanoseconds. Right? And for both CPUs and GPUs. Now, as I mentioned before, how they hide that latency is different, but the time scale is the same. For integer operations, those take a clock cycle or 2 clock cycles, depending on the operation. Again, that's really the same between CPUs and GPUs. GPUs, because they have threads to hide more latency, may have a kind of longer tail on each operation. Like the amount of time it takes to like write back data to the register file and such may take a little bit longer, but generally not much. Now in terms of precision, now of course a long time ago, GPUs didn't support double precision. So again, that hasn't been true for 10 years. The GPUs support double precision just fine at this point. There are some accuracy differences that you may want to keep in mind, although they're not actually specific to GPUs. Most GPUs, for instance, only support one rounding mode. So on most CPUs, you can set the rounding mode. No one actually sets the rounding mode, and please don't. It's an extremely expensive operation. But on most CPUs, you can actually change the floating point rounding mode between like round to nearest or round towards 0 or whatever. On GPUs, they recognize that no one actually does this, and they just only support round to nearest, which is the default. It's also the only unbiased one, so it's the only one you actually want to use in scientific computing anyway. Most CPUs fully implement the IEEE floating point semantics for what are called denormal numbers, which are numbers that have really, really small or really, really large exponents. And many GPUs don't. Some embedded CPUs also don't, like ARM CPUs, for example, that run on your phones, what have you, often also don't implement denormal number handling. And GPUs traditionally have not either. So oftentimes people who complain about the fact that, oh, I ran my code on a GPU and I got a different answer, it actually had to do with denormal numbers more than anything else. But for the kinds of computations they do support, the answer should be the same. Now, that having been said, there is one exception to this, and that is it depends on what kind of computations you view the system as providing. So if you view the system as providing addition and subtraction and multiplication and division and square root, the answer should be the same. If you view the system as providing sine and cosine, for example, well, sine and cosine, the accuracy of those depends on whatever library you're using to implement sine and cosine, which will differ between many different CPU systems as well, because it's actually provided by the C library, not really by the processor. But oftentimes people who say have only ever run their code on a Linux cluster have only ever actually used one sine and cosine implementation. And so they run on a different system and they go, oh, the answer is different. So that's something to keep in mind as well. Sine and cosine, by the way, are not, like their accuracy is not really covered by the IEEE standard. They're also not normally correctly rounded. Like you have to be careful about using those. And the implementation on GPUs can differ from the implementation on CPUs. Another difference that comes up is, of course, if you enable like fast math support. Fast math support will sort of do two things. So one is different compilers do different things with fast math support. Like it might reassociate different operations and give you a different answer. Another issue that comes up with fast math support is it normally enables things like fast divisions and fast square roots. And the way it does that is that it uses the processor's ability to generate a reciprocal or square root estimate and then do some Newton iterations to refine the estimate. And if you need to do a division, which people often, or you know, a square root or what have you, which is actually a quite common operation in scientific computing when you're computing like a radius or something, force, whatever. Then you really do want to use the reciprocal estimates and the Newton iterations, but different compilers and different systems give slightly different answer for the estimates because that's not standard. And so that can also lead to a difference between GPUs and CPUs. It can also lead to a difference between PowerPC CPUs and Intel CPUs, but this is where people often see that come up. On what?
Like the Knight's Landing or in GPUs, what kind of success have other teams had, just to get an idea of what system you want to invest your time in.
So there kind of are statistics. I'm not sure how meaningful they are. The advantage of the Knights Landing systems, for example, is that they're essentially regular Intel chips from the software perspective. And so they can run any software that you can run on any other Intel system. Now, there's a difference between running and running well. So now there are advantages to auto-vectorization on these systems. In fact, the compiler should be able to vectorize more. And I think people have found that to be true. We've actually had a fair degree of success taking applications which previously required a bunch of manual tuning work, and the compiler was able to auto-vectorize the relevant loops when targeting Knights Landing. So we really have been pleasantly surprised as far as that goes. GPUs always require some amount of manual work. They are normally on a sort of system versus system comparison basis. You get more compute capability out of the GPUs. You also might get more memory bandwidth in practice out of the GPUs because of the way that the GPU memory controllers are arranged versus the way that CPU memory controllers are arranged. In the sense that GPUs have more of them and other things. So if you have a code which is if you have a code which will easily map onto a GPU, like there's a lot of parallel work where each of these, say, hardware threads can do the same thing, if that mapping is natural for your algorithm or your code, or you can make it so by an appropriate choice of an algorithm, then you'll often get a lot of, you'll do very well on the GPUs. If that mapping is difficult, then I think you should do a lot of thinking about how much time you want to invest in that. I think that's certainly been a lesson from our porting experience to, say, Titan, which is the GPU machine, which is that on codes where that mapping was very natural, it didn't take a lot of development time to do that, to take the relevant kernels and put them in CUDA or whatever, or use OpenACC once the compilers finally worked, and get good performance. Whereas for codes where that mapping was not very natural, people spent a lot of time trying to port them, and they ended up with very small speedups over running on the CPUs. So I think it really comes down to how well it fits what you're trying to do.
What's the best architecture for particle code? I'll get it right now.
Yeah. I don't know that I can answer that question yet. We've only just started doing some experimentation with Knights Landing. We've had some very good experiences with particle codes on Knights Landing. Particle codes have traditionally also done fairly well on GPUs, and I don't have any experience with the new GPU architectures yet. It also is going to depend on how many particles you have. So if you have a lot of particles and your code is essentially memory bandwidth bound, because your code is really just like streaming in particle arrays and doing a little bit of compute, but you're bound based on that speed, then assuming the algorithm maps cleanly, you'll probably get better results on the GPU, just because the GPUs will be better able to maximize the available memory bandwidth on the system. But with the high bandwidth memory on the Knights Landing, it may not be bad either. If you have a small number of particles, and so it will really fit in cache on either systems or in shared memory, then it'll probably do fine on both, although you may want to arrange the algorithms a little bit differently. Like you may make different choices about whether you're doing structure of arrays versus array of structures on the different systems. The other thing that I'll mention in this regard is on algorithmic choice. So and this also touches on one of the questions about complicated data structures. So one of the codes that I've worked on, HACK, which is a large-scale structure cosmology code, it's a particle code, and on CPUs we have a KD tree-based force solver for the particles, to compute the short-range forces between the particles. Whereas on the GPUs, we essentially just block the particles into small regions and then just do all of the n-squared computations. And this actually works out well because the GPUs have more compute capability, whereas the CPUs are better at executing the pointer tracing operations that you need for the tree data structure. And so the GPU code is actually simpler in that regard, but both work well. Once you sort of choose an algorithm that maps well onto each architecture. Okay. Oh, yeah, go ahead.
Do you have ideas how to cope with the very limited number of registers on GPUs? So the car exceeded the number, what do I do?
So there are two things. So one is if you have a lot of registers on the GPU because you're doing like a lot of computation at one part in the kernel, and then you're using those values later, and so you just have a lot of sort of live values that are flowing through. Then I would think about how you might split up the kernel, and if you're using a lot of registers, one question is, are you actually spilling to the stack on the GPU? Like, are you actually up against the maximum limit? Because if you are, then there's actually no advantage to having them in registers at all. You should just write those values to some intermediate array, and then read them later in a different kernel or in the same kernel. If you're not, then a limited amount of spilling might actually help you. And so you can force the compiler to use a smaller cap on the number of registers. The other thing you might do is think about the algorithm you're using. For example, in in HACS, this particle code that I've worked on, we have a polynomial approximation to the force law that's being solved. And the order of the polynomial approximation is actually something that we can tune, right? There's a trade-off between the resolution we use and the order of the polynomial approximation we use. So we pick the order of the polynomial approximation we use to maximize the register use, but not to exceed the limit of how many registers we have. And then we pick a resolution that works with that polynomial order, whatever order we use. So there's a trade-off there as well that might be relevant for your situation.
All right. Okay, so let's thank you again.